We spent the last couple of days talking about charged particles experiencing magnetic forces in external magnetic fields. Well, those charged particles were just moving through the air. If those charged particles are moving through a wire, then we call it an electric current. They'll still experience a magnetic force, but because they're inside a wire, the wire will also experience a force. So if the particles themselves experience a magnetic force, then the wire that they're contained in will also experience a magnetic force. Before we talk in detail about that, though, we have to define a term, and that is electric current. The reason we have to define this term is because the equation that we're going to use to describe the force on the wire requires us to know what the electric current is. We're going to define current as the rate of flow of electric charge. That doesn't mean how fast the charges are moving. That means how many of them are moving per second. If you had two people on the side of the highway, one person was counting the number of cars that went by every second, and one person had a radar gun out and was measuring how fast the cars were moving, how far they traveled every second, then the current would be analogous to the person counting the number of cars per second. Okay, he or she is not measuring the speed of the cars. He or she is measuring the rate of flow of the cars, how many cars per second are flowing. So electric current is analogous to that. The equation that would describe it is this. I, that's the symbol for electric current, is equal to Q, the amount of charge. This would be analogous to the amount of cars that flowed, that went by, divided by T. Charge, by the way, is measured in what units? Coulombs, yeah. T is time, and it's measured in seconds, of course, yeah. So what units do you think electric current are going to be measured in? Yeah, we could say coulombs per second, absolutely. We see that fairly often, actually, coulombs per second. But what's another set of units that we can use to describe electric current? Amps, yeah, amperes. The symbol for amps or amperes is a capital A. So we would say that 1 amp or 1 ampere is exactly the same thing as 1 coulomb per second. You could be prepared to see either one of those, coulombs per second or amps. All right, we're going to do one quick example on this, and then we're going to keep plugging forward to cover this main concept today, which is the wires, the current-carrying wires in a magnetic field. Here's the first example. It's on page 3 of the booklet that I gave you last week. It says, calculate the electric current in a wire if this many electrons flow through the wire in 7.50 seconds. To find the current, we're going to say it's Q over T. But we don't know Q, do we? Or do we? What's the charge here? What is it? Okay, well, same answer as somebody gave me last class. It's not right. It's not 1.6 times 10 to the minus 19. That's the charge of 1 electron. We don't have 1 electron. What do we got? We got 5.5 times 10 to the 10 electrons. So what are we going to do to find the charge? Multiply them together, right? 5.5 times 10 to the 10 times 1.6 times 10 to the minus 19. Now this is where, however I did this, I'm not sure how I made the mistake, but last class I multiplied these two numbers wrong. I think the correct answer there is, just double check this to make sure I've done it right this time, 8.8 times 10 to the minus 9 coulombs. Is that right? There's our charge. Let's take that number for charge and let's divide it by the time, which is 7.50 seconds. When we do that, we get a value of 1.17 times 10 to the negative 9 amps. So our electric current here is, remember, not the speed of these charges, but rather how many of them are flowing per second, is 1.17 times 10 to the negative 9 amps. Okay, this says nothing about the speed, right? The speed of the particles could be slow, could be fast, whatever. Just like when you have a bunch of cars going by you on the highway, they could be going slow or they could be going fast. The number of cars per second says nothing about how fast they're moving. All right, well, let's take that then and apply it to the main concept of the day, which is what happens to the wire that they're flowing through when that wire is exposed to an external magnetic field. A wire we'll define as simply a conductor, or a current-carrying wire, I should say, we'll define as a conductor with electrons flowing through it. Simple as that. Instead of the electrons flowing through the air, they're flowing through a wire. We call it an electric current. Now, if those electrons, whether they're in the wire or not, are moving through a magnetic field, they'll experience a magnetic force, according to the hand rule for deflection that we learned about a couple days ago, and according to the F is equal to QVB equation. We can find the magnetic force on an individual electron moving through the air or moving through a wire by using those two things, the hand rule for deflection and the equation F is equal to QVB. But if that electron, or if multiple electrons experience individual forces while inside a contained space like a wire, then that wire is going to experience a force as well. It's like you've got individual molecules within a bubble, individual molecules all experiencing a force. What's going to happen to the bubble? Well, it's going to experience a force as well. Okay, if you have individual objects within something experiencing a force, and they can't leave the object, can't leave what they're contained in, then the object that they're contained in will also experience a force. But we're not going to describe the force on the conductor with the same equation. The direction of the force on the conductor will be the same as the direction of the force on the individual particles. We're going to use the hand rule for deflection to find that. But to find the magnitude of the force, we're going to need to learn a new equation. You can write this page down or not, guys, because this is just the exact same summary that we gave you for the force on a moving charge through a magnetic field, right? It's the hand rule for deflection. If you've got charged particles moving through a wire, okay, and we want to find the force on the wire, do the exact same thing as you did for the individual charges. Thumb in the direction of the particles or the direction of the current, fingers in the direction of the external magnetic field, palm's going to point in the direction of the magnetic force on the individual particles and on the wire itself. One thing to note here, the individual particles want to go in a circle, right? But because they're inside the wire, they can't. So there's just going to be a force like downward or upward or outward. It's not going to, the wire's not going to go in a circle like the individual particles would if they were free to move in a circle. But the direction of the force would be the same. All right, what about the magnitude of that force now? The magnitude of the force on the individual particles was QVB. The magnitude of the force on the wire is ILB. Okay, F, of course, means the magnetic force, and the units for that are going to be newtons. I stands for, just learned this, I stands for, the electric current, which is measured in amps. B stands for the magnetic field strength, and the units for that are going to be Tesla. What does L stand for, you think? What's L stand for? It's the length of the wire in the magnetic field. So if you have a 3-meter long wire, but only 1 meter is in the magnetic field, what length would you use? If you have a 3-meter long wire, but only 1 meter is in the magnetic field, what length would you use? 1, not 3, right? Now, there's one other important part to note here. There should be a little upside down T here. So we may not even use the 1 unless it is perpendicular to the field. If you have 3-meter long wire, 1 meter is in the magnetic field, but half of that is parallel to the field, then you're only going to use 0.5. Because what we care about is the length of the wire that's in the field and is perpendicular to the field. And that length of wire is going to be measured in meters. Question number, this is example number 2 on page 3 of the booklet that you got last week. It says a 10 centimeter long wire, whoops, what happened there? A 10 centimeter long wire carrying electron current into the page lies in a magnetic field that is 0.2 Tesla to the left of the page. By the way, this number is not in your example. This was a typo that I made that I added when I realized that, but I already had yours photocopied. So please add that number. The external magnetic field is 0.02 Tesla. Please add that to your example question. It should have been a given. It just wasn't, because I didn't notice it until I went to do my answer key, which is after I photocopied your stuff. To the left of the page, this many electrons flow through the wire in 10 seconds. What's the magnitude of the magnetic force acting on the wire as a result of the external magnetic field? Listen, if we want to find the magnetic force on a wire, we're going to say F is equal to ILB. We need the current. We don't have the current, so let's find it. Current is Q over T. We don't know the charge, so let's find the charge. It's 8 times 10 to the 19 times 1.6 times 10 to the minus 19. And I think when we do that, that we end up getting 12.8 coulombs. Is that correct? Which we're going to divide by the time. 12.8 coulombs divided by time of 10 seconds gives me 1.28 coulombs per second, or amps, which we're now going to take and multiply by L and B. 1.28 times L, make sure you put that in meters, 0.10, times B, 0.02. Yours says 8.0 times 10 to the 14. Well, so just got pointed out to me that there's another typo there. On your sheet it says 10 to the 14. We're going to make it 10 to the 19 to make this correct, okay? 10 to the 19 electrons. So everything we have up here is correct based on the data that you see in this question. It's just you have to make your question agree with this one. Okay, we multiply these together. We end up getting, I believe it's 2.56 times, I think, times 10 to the minus 3 newtons. Now, what's the direction? The electron current is going into the page, left thumb into the page. Magnetic field is pointing towards the left of the page. So thumb into the page, fingers left of the page, palm points down the page, down the page. Or you could say toward the bottom of the page. Just don't say down, right? Your page is your frame of reference. It's down the page. It's toward the bottom of the page. Okay, let's do one more example question. Number 3, it says a 45 centimeter long wire. Let's convert that to meters. This mass lies perpendicular to a magnetic field. Okay, perpendicular, that's good. All the stuff we've learned is valid. Here's an electric current flows through the wire. What's the magnitude of the magnetic field necessary to cause the wire to be suspended in the Earth's magnetic field? Okay, this is an addition to your question as well. This isn't on your page, but just make sure that it says the Earth's magnetic field. What's the key word here? Key word or key phrase? Suspended. Suspended means, look at our thesaurus over here, suspended means undeflected, F net is 0, balanced forces, equilibrium. If we have a magnetic force in the Earth's, this should say, not magnetic field, gravitational field. If we have a magnetic force, magnetic field, and a gravitational field, then the two forces that are going to balance are Fe. Well, let's not say Fe. Let's make it Fm. Unless you want to make the magnetic force called Fe for some strange reason. Fm is equal to Fg. We're going to say QVB, or not. How about ILB is equal to M times G. All right, we're looking for the magnetic field necessary here. So we're going to say B is equal to mg over I times L. M is 3.5 times 10 to the minus 2 kilograms times G is 9.81 divided by the current, which is 0.220, times the length of the wire, which is 0.45 meters. Make sure you put that in meters, right? Do the math here, and it should work out, I believe, to be 3.47 Tesla. That's a pretty strong magnetic field, right? But it's possible. In order for this wire to just be suspended, to hover, to levitate in the Earth's gravitational field, you'd have to have a pretty strong magnetic field. But it would be possible, okay? Because this is, what do we say the strongest human-made magnet ever is 40, something like 40 Tesla? Hey, we could do that. Just be hard, that's all. Your homework over the weekend is worksheet number 13. I think there's only 5 questions on that, so it shouldn't take you an exorbitant amount of time. Make sure you get that done for Monday, please.